In social science statistical research, you have probably learnt, or at least heard of, t-tests, ANOVA, and normal linear regression. Let's start with the bad news and then move on to the good news. The bad news is that traditional methods are difficult to use. Traditional methods like t-tests, ANOVA, and linear regression can be tricky to learn and difficult to apply. When you're subtracting one mean value from another and then dividing by a standard deviation, you have probably asked yourself, wait, before I divide by this number, do I need to calculate its square root or not? You're faced with pages of equations and tables of z values and t values. It is all too easy to make a mistake. Traditional methods are very old and often misleading. These techniques are old, very old. T-tests were developed in 1908 and ANOVA was first published in 1921. They predate computers. Let me repeat that. These data analysis techniques predate computers. They were designed to be completed by hand. Back in the day when things had to be calculated by hand, certain simplifying assumptions had to be made, such as that values are normally distributed. T-tests, ANOVA, and linear regression require these assumptions to be at least approximately true. To the extent that the assumptions aren't true, the conclusions you draw from the techniques are misleading. Like you, companies such as Google and Amazon need a keen insight into human behavior to understand how people will respond to different product offers, different color schemes, different web layouts, etc. Do you think they use t-tests and ANOVAs when they mine customer data to work out what products to sell you next, or what online advertisement to show you to get the best response rate? The only rule or regulation they are bound by is to use whatever technique works best. When profits are on the line, companies constantly innovate and use the best predictive and statistical techniques they can. They don't use t-tests or ANOVAs in their predictive analytics. Contrast this against conservative institutions that are driven by 50-year-old rules, regulations, and standards that say, when writing a research report, you need to present ANOVA and t-test tables in this format. The implicit assumption in these rules, regulations, and standards is that ANOVA and t-tests are the best techniques to use, but more advanced techniques have been available for decades. Number 3 is that traditional methods don't produce a predictive model. Because these techniques were designed to be calculated by hand, they were very narrow in what they were designed to do. In survey data, you might test for differences in response by sex, then do another test for difference by age, and then another one for differences by nationality. In its basic form, each test doesn't naturally allow for the simultaneous effects of other predictive variables, nor do they naturally indicate mediating and moderating variables. You have to do separate, quite complicated tests for those. And then doing those tests, each predictor still mainly gets marked on a pass-fail basis. Let's say you conduct an experiment to see how likely someone is to respond to a command. Are certain groups of people more likely to respond? Is there a difference in response rate by sex, or isn't there? Is there a difference in response rate by age, or isn't there? If you want to know how much of a difference being male or female, or young or old makes, you then need to do a separate calculation for effect size. And then you end up with an effect size number like 0.4. Is 0.4, is that a lot or not? What you really want, what would be useful is, once you have calculated your survey data over, say, 100 individuals, is to build a predictive model. Such a model will firstly show you that being male or female does make a difference to the response rate, but say age makes no difference, and then the effect of being male, after allowing for all other characteristics at the same time, increases the response rate by 5% or decreases it by 10%. This 5% or 10% impact is intuitive and interpretable by an average person without training in interpreting effect size values or looking them up in a textbook. There's no need to calculate an effect size and look up what that number actually means. As humans, we can interpret what a 5% or 10% change in response rate means with little effort. Building such a model is a massive leap forward on traditional statistical approaches in psychology and the social sciences. You still cover off your statistical tests. work out which predictor variables are significant and what aren't, but at the end of the process, you end up with a coherent predictive model. This model has intuitive parameters that can be generalized to make predictions for specific cases in the general population. You can predict how likely these new individuals are to respond to the command, or how likely they are to buy a product, or what someone's social connectedness will be, or how likely they are to die in the next 12 months, or whatever it is you're trying to predict. The good news is that there are advanced modern approaches out there that are easy to use, easy to interpret, are far more statistically and scientifically rigorous than older approaches, and that produce useful predictive models. Preddle uses these techniques. Preddle is very easy, intuitive, and graphical. Preddle is much easier to learn than traditional statistical approaches. It is primarily graphical. You'll be working with charts, although you won't need to calculate equations. The same statistics, such as confidence bands, z-values, and so on, are available. The approaches we use in Preddle are more statistically rigorous than traditional techniques. The predictive analytics field has benefited greatly from increased computing power. The less time a researcher needs to spend on tedious calculations, the more time they can spend on interpreting the output, thinking about how it fits into the bigger picture of theories of human behavior and how best to apply the research in improving the welfare of mankind. Preddle is modern and statistically rigorous. Preddle uses GLMs, or generalized linear models, and regression trees. Note that generalized linear models are not the same as general linear models. Confusing, I know. GLMs are an advanced form of multivariate linear regression, of which the theory dates back to the early 1980s. GLMs are very statistically robust and okay to use even when your data is not normally distributed. Regression trees are constantly being researched and improved even today. Both techniques are used extensively in industry for predicting how customers will behave. They are popular because they work, and they work well. Preddle produces predictive models. In addition to testing for effects, Preddle will also produce a predictive model. To demonstrate, let's use an example such as an experiment testing whether someone will respond to a command. Say that if someone is an employed male, age 30, their probability of responding is 0.2. If they are unemployed, we multiply this probability by 1.2. Or if they are 40 years old, we multiply the probability by 1.3. And if they are both unemployed and 40 years old, we multiply the probability by both 1.2 and 1.3. But if they are female, we multiply the probability by 0.75. Since we now have a set of factors spanning combinations of sex, age, and employment status, for any individual's combination of these characteristics, we can multiply the appropriate factors together to predict what their expected response rate would be. The great thing about building up a predictive model this way is that during the model building process, all factors are automatically tested simultaneously. Maybe age looks significant by itself, and maybe employment status also looks significant by itself. But when you put them together in the same model, suddenly age isn't significant anymore, because any effect on the response variable is actually fully explained by employment status. Once employment status is included, age provides no additional predictive power. Maybe employment status acts as a mediating variable for age, so you can drop age from the model. This would never have become apparent by testing each one separately with a t-test or ANOVA. Finally, Preddle output is consistent with APA standards. The human brain likes charts better than tables of numbers, but reporting standards often require tables. Luckily, you can take advantage of the charts to build the best model you can, and then at the very end, you can copy the figures for your research report. GLMs and regression trees are an advanced form of regression, So APA standards on regression would apply.